Here we are together again to study a new topic: engine operation. Let's start immediately by defining that diesel is a mixture containing aliphatic hydrocarbons from 13 to 18 atoms and paraffins. By aliphatic, we simply mean a compound in which the molecules are made up of an open chain of carbon atoms. The paraffin, on the other hand, is a substance that freezes below 2 degrees Celsius, creating problems with the flow of diesel to the engine and prevents the fuel filter from functioning properly, as well as clogging the fuel and injection ducts. If this problem occurs, it would be necessary to wait for the hottest hours of the day to start the engine. There are also types of additives, such as antifreeze, which have the function of dissolving the paraffin, making the diesel more fluid. Keep in mind that fuels often contain impurities that the filters are unable to completely retain. Therefore, the injectors tend to get dirty and clogged. If this happens, the injection does not take place regularly, and we could encounter problems such as excessive fuel consumption, loss of performance, increase of harmful substances in the exhaust gases, irregular idling, difficulty in starting the engine, and in the long run, serious problems with the engine. Consequently, we understand how important the maintenance of a vehicle is in preserving the reliability and longevity declared by the car manufacturers. Diesel engines exploit compression to spontaneously ignite the air-fuel mixture. This is the theoretical basis of the process that initiates combustion. The engine needs a certain amount of air and fuel inside the combustion chamber in order to start combustion as efficiently as possible. Remember that carburation is an index that represents the quality of combustion and is defined as complete combustion, when all the fuel has been burned and there is no unburned fuel in the exhaust gases. To correctly balance the chemical reaction, we have a specific air-fuel ratio that we represent in this way. This simple division defines the quantity of mass of air necessary to completely burn a certain amount of fuel. This value is called the stoichiometric air-fuel ratio. By changing the fuel, there will be different stoichiometric, ideal air-fuel ratios. For diesel engines, this value corresponds to 14.5. So, to have complete combustion in a diesel engine, we need 14.5 kilograms of air to completely burn 1 kilogram of fuel. Translated into milligrams, we will respectively need 14.5 milligrams of air for each milligram of fuel. Now you are probably wondering how our engine control unit measures these values and understands the amount of fuel needed. Simple. Thanks to a sensor positioned in the exhaust manifold that measures the oxygen present in the exhaust gases called oxygen sensor, or more commonly, lambda probe, the percentage of oxygen remaining after combustion is detected and allows the control unit to instantaneously calculate this so-called instantaneous air-fuel ratio, which defines the air-fuel ratio. This allows the engine control unit to determine if there is excess air in the mixture or if there is too much or too little fuel injected. The ECU reads this measurement and adjusts the amount of fuel continuously injected to keep the mixture as close as possible to the stoichiometric air-fuel ratio value corresponding to 1.0. The lambda value, by definition, is a mathematical calculation between the available air mass and the air mass required for combustion, which is calculated as a division between instantaneous air-fuel ratio value and stoichiometric air-fuel ratio value. Let's list in detail the lambda values that the ECU can calculate internally. Lambda equals 1 occurs when the combustion is stoichiometric, or rather, all the fuel participates in combustion. Lambda is less than 1. In this case, we have an excess of fuel, meaning the unburned fuel in the exhaust gases, which creates more pollution. This is called rich carburation. Lambda is greater than 1. Here we have an excess of air compared to the injected fuel, and consequently, high temperatures and a higher concentration of nitrogen oxides. It is defined as lean carburation. Perhaps an example will help you better understand how air-fuel ratio works, allowing you to apply the formulas discussed above. Let's open the map relating to the torque limiter used by the manufacturer to limit the maximum torque that can be delivered by the engine. In our case, the maximum torque is 2,400 RPMs and corresponds to 257 Newton meters. We now understand how much fuel the ECU must control according to the engine torque to be generated. We check the maps that allow conversion of the torque into fuel, and which are called quantity of fuel injected. In our case, at 2,400 RPMs and 257 Newton meters, we make the mathematical average and find about 43.27 milligrams of fuel. So, by interpolation between columns 250 and 280 Newton meters and between lines 2,250 and 2,500 RPMs. Now let's open the map called quantity of air, which allows us to understand better. For 2,400 RPMs and 257 Newton meters, we find about 989.018 milligrams per stoic A. Interpolation between 2,250 to 2,500 RPMs and 240 to 280 Newton meters. So now let's apply the formulas seen above. Dividing the milligrams of air we found, 989.018 milligrams, divided by the amount of fuel used, 43.27 milligrams, to get the correct instantaneous air-fuel ratio at 2,400 RPMs with 257 Newton meters. Now we can get the correct measured lambda value instantly, that is, 1.575. You should know that one of the main problems of diesel engines is created when the carburation is excessively rich. This means that there is a lot of fuel in the exhaust gases. As a result, a very high level of particulate matter is formed, which would prevent automotive groups from complying with emission laws. Conversely, by using too lean a carburation, there will be a tendency to produce more pollutants, such as nitrogen oxides. This carburation in some cases could also cause relatively low performance, as well as possible engine damage. According to the various operating conditions, the ECU can mandate other injections in addition to the main one, in order to enrich or lean the carburation. Since this is a fundamental topic, we will better analyze the pre- and post-injections in another chapter of our training course. But it is important to understand why the ECU can use various carburations: to reduce emissions in order to pollute less and comply with emissions laws. The ECU commands post-injections in order to increase the exhaust temperatures and consequently allow the regeneration of the particulate filter. For consumption, if, for example, we stop at a railway crossing with the engine running, the ECU will try to limit consumption as much as possible by injecting less fuel. To facilitate ignition, in the event of low or different atmospheric temperatures where ignition problems may occur, the ECU controls pre-injections by heating the combustion chamber so as to facilitate vehicle ignition in this case. To increase or decrease the vehicle's performance, if we ask for more or less performance by using the accelerator pedal, the ECU will command more or less fuel in order to increase or decrease performance. Now that you understand why the ECU can use different carburations, let's talk about the treated fuel, which is part of the family of liquid fuels, or rather, diesel. The density is equal to 0.848 to 0.860 kilograms per liter. This means that, for example, if we put the same amount of diesel in a glass of water with a density of 0.997 kilograms per liter, the latter will float on the surface since having less density, meaning that it is lighter than water. The flash point is the lowest temperature at which diesel fuel produces enough vapor to create a flammable mixture in the air. The lower the flash point temperature, the easier it is to ignite the air in cylinders. Conversely, the higher the flash point, the safer the fuel is to handle. For diesel, it appears to be above 53 degrees Celsius. So if the temperature of the diesel oil is lower than this value, ignition does not take place. The calorific value is the quantity of heat expressed in kilocalories, which develops from the complete combustion of 1 kilogram of fuel. The calorific value is the element that better than any other characterizes the value of a fuel. For diesel, it is 41 to 44 megajoules per kilogram. Finally, the self-ignition temperature is the lowest temperature at which fuel ignites spontaneously in a normal atmosphere without a flame or spark. This temperature is necessary to supply the activation energy and thus start combustion. The temperature at which a chemical ignites decreases with an increase in pressure or oxygen concentration. For diesel, this happens when the temperature is higher than 210 degrees Celsius, about 410 degrees Fahrenheit. Curiosity. When we talk about self-combustion in a diesel engine, it means that in extreme conditions, in the event of the vehicle overturning, breaking the turbine, excessive rise in the engine oil level, or if a component near the fuel tank overheats and causes the fuel to reach temperatures above 210 degrees Celsius. This could cause self-combustion, a very dangerous factor, since the flames become unmanageable as they are self-powered by the heat generated. You must know that the combustion in diesel is characterized by a lean air-fuel ratio to optimize engine operation. To avoid excessive formation of pollutants, the air-fuel ratio at maximum torque is usually kept around 20 to 25, well above the stoichiometric air-fuel ratio that we saw earlier, corresponding to 14.5. The excess air present in the cylinder after the combustion of the fuel continues to mix with the active gases in combustion and with those already burned during the combustion and expansion processes. It is good to remember that, to vary the engine speed, the stoichiometric ratio between air and diesel fuel can be changed. The more diesel fuel enters, the more powerful the combustion chamber will be. Therefore, we will have greater thrust on the crankshaft and an increase of revolutions per minute. Furthermore, most of the air introduced into the cylinder of a diesel engine is compressed and heated, but it never intervenes in the combustion process. Excess oxygen in the air helps oxidize gaseous hydrocarbons and carbon monoxide, reducing them in the exhaust gases. It should be noted that in order to always function in a state of excess of air, most diesel engines are equipped with a turbocharger. This takes care of recovering energy from the exhaust gases to use it during intake. Once emitted, the exhaust gases generate energy which will then be transported to the turbine, whose mission is to recover part of this energy and then return it to the compressor. The air generated by the compressor is used to supply excess air, which will allow the engine to run on lean carburetions. On diesel engines, we can find different types of turbochargers, but the one currently used is the variable geometry turbine, which has the task of regulating the boost pressure at various driving speeds. By changing the position of the vanes, the boost pressure varies because the thrust and speed of the exhaust gases varies according to the opening of the vanes. This leads to better pressure adaptability across all engine speeds and better driving dynamics than a fixed geometry turbine. We sometimes also find a wastegate valve which, pneumatically or electronically operated, decreases the internal pressure of the compressor. Let's now analyze the consumption of some diesel engines since, when it comes to fuel, things are not always the same. 1 liter of diesel contains about 15 to 20% more energy than a liter of gasoline, which means that a diesel vehicle would travel longer on a full tank. But what about efficiency? Let's consider the difference in energy density of the fuel and the efficiency of the engine itself. The efficiency generated by the diesel engine is 20 to 25% higher than the petrol engine, and this means that the diesel allows you to travel more kilometers, consequently allowing a considerable economic savings. Conversely, the heavy molecular structure of diesel requires more heat than a petrol engine to trigger combustion within the combustion chamber. However, The exhaust gas temperatures of a diesel engine are considerably lower. They are in the 400 degrees Celsius range and 500 degrees Celsius under normal operating conditions, while under the same conditions, a petrol engine reaches 600 or 700 degrees Celsius. Here we are at the conclusion. But before saying goodbye, let's do a brief recap of the topics we talked about. We have seen how diesel engines work in states of excess of air, and we have understood how the control unit manages to always regulate the carburation, making it more efficient in order to maintain and not to produce excessive quantities of pollutants. Finally, we have detailed other technical characteristics of the fuel used in diesel engines and understood how it can always work in excess of air. In the next video, we will go into greater detail to understand how the ignition advance works and how it affects the ignition. See you soon!